Welcome to week 12 of this course. In this week, we will start with analysis of composite beams. So far the analysis of composites that we have done are for laminated plates. So they are dominant in both the in-plane directions x and y. Now in case of beams, there is only one it is the dominant only in direction x, and accordingly the analysis is adjusted. So this is how a beam is. Its width is much less than length. So dimension along x is much higher than dimension along y. Now again, depending on the lamination sequence, these beams can be symmetric or anti-symmetric. So for simplicity, let us start with symmetric beams. So beams with symmetric layup. Now because it is symmetric, we know B matrix is 0, and so the in plane equations and out of plane equations are uncoupled, and this beam is under transverse load. So under transverse load, that means load along z direction. So we are studying the bending of it. Now because it is under bending and the laminate is symmetric, we will see only bending. So there will not be any extension or contraction or in plane shear. So we can write the uncoupled equations, the moment resultants mx, my and ms as D matrix multiplied by kappa x, kappa y and kappa s, and we know that these kappas are the second order derivatives and mixed derivatives of w. So we have minus del 2 w by del x 2 minus del 2 w by del y 2 minus del 2 w by del x del y. So we can invert it and write as now B matrix is 0, so inversion is easy. So we get a small d matrix here and we get mx, my and ms, and where small d matrix is inverted version of the capital D matrix. So here w is a function of both x and y. So also we consider pure uniaxial flexure, and that makes mx not equal to 0, but my and ms equal to 0, and that makes the analysis somewhat simpler. So with this assumption, this equation can be rewritten as minus del 2 w by del x 2 minus del 2 w by del y 2 minus twice of del 2 w by del x del y, and we have D matrix here and we have mx 0 0. So now with this we can write minus del 2 w by del x 2 is equal to dxx mx, and here we have minus del 2 w by del y 2 is equal to dxy mx. Remember, D matrix is symmetric, and we have minus twice of del 2 w by del x del y is equal to dxs mx. Now, these moments are moment per unit length. Now, in a beam generally we talk about the moment itself, that means the moment multiplied by this dimension. So, if we say that this dimension along y is b, then the total moment becomes mx into b. So, total bending moment becomes m is equal to mx multiplied by b. Now, we know from the moment curvature relation that m, which is equal to mx b here, is equal to minus ex I del 2 w by del x 2, that we know from our beam theory. And again these are all Euler Bernoulli beams, that means there is no shear deformation. So, and that is why we are using the equations that we got from the classical laminate theory, because that also assumes no shear deformation. And from this equation we have got mx is equal to minus 1 by dxx del 2 w by del x 2. So, with this we can write exi as exi as b by dxx, and that gives us Ex equal to 12 by h cube dxx, because we know that I, second moment of inertia with respect to y axis, is b h cube by 12. So, our beam has a thickness h. So, dimension along z is h. So, for a rectangular section, the moment of inertia I with respect to y axis is b h cube by 12. So, if I use it here, finally Ex comes out to be this. So, we are trying to find out an equivalent quantity that we generally use in beam theory, that is that. So, for that we are using, I mean that we are finding out by these roots, we are getting Ex as this. Now, we need to find out the stresses. So, to find the stresses, all we need is, we need to find out the strengths first, and here there is no in plane deformation. So, entire thing is due to curvature only. So, we have z into kappa x, kappa y, kappa s, because epsilon x 0, epsilon y 0 and epsilon s 0 are 0. So, after we got this, then we can write stresses as sigma x, sigma y, sigma s for the kth layer. So, it is at the kth layer. So, our beam has several layers. So, layer 1 to layer n, and the height is h. So, this is direction x, this is direction z. So, by using the constitutive relations, we can write this as this matrix Q in the XY system for the kth layer multiplied by Z is already there. So, multiplied by kappa x, kappa y and kappa s. Now, we can combine these equations. So, we can combine whatever kappas we have got. So, here we have got the kappa. So, this is nothing but kappa x, this is kappa y and this is kappa s. So, from here these equations we can get the kappas in terms of mx, and from here we can get the stresses in terms of kappas. So, finally, after doing all these things, after combining all these equations, what we get is sigma x at the kth layer is equal to z multiplied by qxx for the kth layer multiplied by dxx plus qxy for the kth layer multiplied by dxy plus qxs for the kth layer multiplied by dxs into m by b. And then we can write this as z into f1 k into m by I. So, here where f1 k is equal to qxx for the kth layer into dxs plus qxy for the kth layer into dxy plus qxs for the kth layer into dxs. Now, similarly, so this is basically rewriting this equation in a compact form like this. Now, similarly, we can write sigma y for the kth layer as z into f2 for the kth layer into m by I, where f2 for the kth layer is qxy for the kth layer multiplied by dxs dxx plus qyy for the kth layer multiplied by dxy plus qys for the kth ply multiplied by dxs, and sigma sk can be written as z into f3k into m by y, where f3 for the kth layer can be written as qxs for the kth layer into dxs plus qys for the kth layer into dxy plus qss for the kth layer multiplied by dss. So, that is how we find out the normal stresses in each ply. Now, we know that in case of composites normal stresses have jump between two layers, and that leads to interlaminar shear stresses. Okay, so, before going to that, just one thing: for isotropic, beams, we have f1 k is equal to 1 and f2 k and f3 k is equal to 0. So, that is why when we analyze an isotropic beam, we do not see any stresses in y direction, or we do not see any in plane shear stresses. Okay. Now, we let us go to the interlaminar shear stresses. So, the interlaminar shear stresses would be found out with the help of the elasticity equations. So, as per theory of elasticity, we know that del sigma x by del x plus del tau x y by del y plus del tau x z by del z is equal to 0 when there is no body force, and this quantity is just sigma x x. We are writing one subscript here, and similarly we know that del tau y x by del x plus del sigma y by del y plus del tau y z by del z is equal to 0, and we have del tau z x by del x plus del tau y x del tau z y. Del tau z y by del y plus del sigma z by del sigma z by del z equal to 0. Now, here we will use this equation, and from this equation we can find out the tau x y. So, for that what we do is, so from this equation we already know sigma x. So, tau x z can be found out as minus h by 2 to z k minus z into f 1 k by m by I and del and dz. So, here again say this is the kth layer. So, we have z k and this is z equal to 0, this is z equal to h by 2, this is z equal to minus h by 2. So, we are integrating from minus h by 2 to our desired z, and we are finding out tau x z by integrating. Now, okay, so just one thing here, this is going to be, because we are integrating this. So, this differentiating this with respect to x. So, this quantity is going to be dm by dx. And then we have 1 by I and dz. Now, we will see one example. So, for example, let us take a bending of a laminated simply supported beam under transverse load. So, let us assume that we have a beam, and this beam is simply supported and it is under load, under distributed load P. And P is not a function of x. So, P is constant P, and the length of the beam is L. So, the support reactions, as we know, they come out to be P L by 2 and P L by 2. So, bending moment at a particular x is minus del 2 W by del x 2 is equal to 1 by E x I and then we can write PL by 2 x minus Px square by 2. So, we are just using the equation that we derived before. So, we are just using this equation and then from there we are writing this. So, this equation we are using and Ex is found out to be this. Now, we can integrate this equation and that gives us minus del w by del x is equal to 1 by E x I, and that becomes P L x square by 4 minus P x cube by 6 plus C 1, and we can integrate once more and that gives us. So, let us absorb the negative sign in the right hand side this. So, and constant is a constant. So, we do not need to change the sign, negative sign is already there, and then this becomes w is equal to minus 1 by E x I into P L x cube by 12 minus P x to the power 4 by 24 plus C 1 x plus C 2. Now, let us put the boundary conditions. So, at x equal to 0 we know w equal to 0, and at x equal to L we know w equal to 0. So, if I use these boundary conditions, we can evaluate C 1 and C 2, and if we do that then W x comes out to be minus P L to the power 4 by 24 E x I 2 x by L cube minus x by L to the power 4 minus x by L, and then we can say that the maximum deflection. So, W max occurs at center means x equal to L by 2, x equal to L by 2, and that W max comes out to be 5 P L to the power 4 by 384 E x I. Now, we can find out the normal stress using the relations that we derived. So, normal stress at x equal to L at kth ply is found out to be sigma x at the kth ply x equal to L by 2, it is equal to L by 2. We are finding out at the center, and that is where the bending moment is maximum, and that is where we get maximum normal stress F 1 k P L square by B h cube. So, this was one example. Now, let us look into another example, that is a cantilever beam under point load. Laminated cantilever beam under point load at tip. So, we have a beam like this made of composite, and it is loaded at the tip by a force P. So, here again we know that bending moment is equal to minus P into L minus x, and so we can write minus del to W by and del x2 is equal to minus 1 by Exi into minus PL plus Px, and then after integrating we can write del W by del x is equal to minus 1 by Exi is equal to minus PLx plus Px square by 2 plus a constant C1, and then we get W is equal to minus 1 by Exi, and here we have minus PLx square by 2 plus P x cube by 6, not 3, 6 plus C1x plus C2. Now, we know that at x equal to 0, W is 0 because it is cantilever beam, and at x equal to 0, del W by del x equal to 0. So, with that we can evaluate C1 and C2, and then we can write the deflection as a function of x as minus PL cube by 6 Exi multiplied by minus 3 x by L square plus x by L cube, and then we can write tip deflection, that means deflection at x equal to L. So, this beam has a length L. So, tip deflection is PL cube by 3 Exi, and at the fixed end that means at x equal to 0 we have bending moment maximum. So, there stress at the kth ply at x equal to 0 that is found out to be ZF1K 12 PL by BH cube. So, this was all these examples that we did that are based on the assumption that beam has a symmetric layup. When the beam has asymmetry in the stacking sequence, we need to do some more advanced treatment. So, we will see that in the next class. So, let us conclude this class here. Thank you.